Welcome to Advanced Learning Tutoring. This is the chemistry playlist. Please like this video and subscribe to our channel. The Earth's resources and potable water. Natural resources, supplemented by agriculture, provide food, timber, clothing and fuels. Finite resources, which is a resource that is running out, include crude oil, which is a fossil fuel. Potable water is water that is safe to drink. Potable water is not pure water in the chemical sense because it often contains dissolved substances. There are a number of methods used to obtain potable water. The methods used to produce potable water depend on available supplies of water and local conditions. In the UK, rain provides water with low levels of dissolved substances. Fresh water collects in the grounds, in lakes and rivers, and most potable water is produced by passing the water through filter beds to remove any large solid materials, and then sterilising with the use of chlorine, ozone or ultraviolet light. When sterilising, this kills bacteria in the water, making it safe to drink. If supplies of fresh water are limited, desalination of salty water or seawater may be required. Desalination can be done by distillation or processes that use membranes, such as reverse osmosis. These processes require large amounts of energy and in turn are quite expensive. The countries that require the desalination process of seawater are those countries that typically have low levels of rainfall. Potable water required practical. Analyse samples of water from different sources in terms of pH and the presence of dissolved solids. To distill seawater to obtain potable water. For each sample of water you are given, test the pH using either a pH meter or universal indicator. For each sample of water, pour 50 millilitres into a clean, pre-weighed evaporating basin. Heat gently over a Bunsen burner, tripod and gauze until no liquid remains. Allow to cool, then re-weigh the evaporating basin and calculate the mass of solid that remains. Wastewater treatment. Urban lifestyles and industrial processes produce large amounts of wastewater that require treatment before being released into the environment. Sewage and agricultural wastewater require the removal of organic matter and harmful microbes. Industrial wastewater may require the removal of organic matter and harmful chemicals. Sewage treatment includes a screening process to check first what the sewage contains, to decide on the following steps. Sedimentation to produce sewage sludge and effluent. Sedimentation is a process where you allow the water to settle. Solids will settle at the bottom, leaving the effluent water at the top. Anaerobic digestion of sewage sludge and the aerobic biological treatment of the effluent. Alternative methods of extracting metals. Previously, we have looked at extraction of metals, which include the processes of electrolysis and displacement with carbon. Copper ores are becoming scarce, and new ways of extracting copper from low-grade ores include phytomining and bioleaching. Low-grade ores mean there is a relatively low percentage of the metal compound within the rock. These methods avoid traditional mining methods of digging, moving and disposing of large amounts of rock. Phytomining uses plants to absorb metal compounds from the soil. The plants are harvested and then burned to produce ash that contains metal compounds. Bioleaching uses bacteria to produce a leachate solution that contains metal compounds. Life cycle assessments and reducing use of resources. Life cycle assessments, or LCAs, are carried out to assess the environmental impact of products. The reduction in use, reuse, and recycling of materials by end users reduces the use of limited resources, use of energy sources, waste and environmental impacts. Metals, glass, building materials, clay ceramics and most plastics are produced from limited raw materials, such as crude oil. Much of the energy for these processes comes from limited resources, such as the burning of fossil fuels, to release energy. Obtaining raw materials from the earth by quarrying and mining causes environmental impacts, such as loss of habitat for animals. Some products, such as glass bottles, can be reused. Glass bottles can be crushed and melted to make different glass products. Other products cannot be reused and so are recycled for a different use. Metals can be recycled by melting and recasting or reforming into different products. The amount of separation for recycling depends on the material and the properties required of the final product. When deciding and looking at a particular product for a certain use, it's important to look at the raw material where each product comes from, the disposal at the end of the life, the use and the operation during its lifetime, and the manufacturing and packaging processes. Using materials. Corrosion is the destruction of materials by chemical reactions with substances in the environment. Rusting is an example of corrosion. Both air and water are necessary for iron to rust. Corrosion can be prevented by applying a coating that acts as a barrier, such as greasing, painting, or electroplating. Aluminium has an oxide coating that protects the metal from further corrosion. Some coatings are reactive and contain a more reactive metal to provide a sacrificial protection. For example, zinc is used to galvanize iron. Most metals in everyday use are alloys. A reminder that an alloy is a mixture of metals. Bronze is an alloy of copper and tin. Brass is an alloy of copper and zinc. Gold used as jewellery is usually an alloy with silver, copper and zinc. Steels are alloys of iron that contain specific amounts of carbon and other metals. High carbon steel is strong but brittle. Low carbon steel is softer and more easily shaped. Steels containing chromium and nickel, stainless steels, are hard and resistant to corrosion. Aluminium alloys are low density. Ceramics, polymers and composites. Most of the glass we use is soda lime glass, made by heating a mixture of sand, sodium carbonate and limestone. Borosilicate glass, made from sand and boron trioxide, melts at a higher temperature than soda lime glass. Clay ceramics, including pottery and bricks, are made by shaping wet clay and then heating in a furnace. The properties of polymers depend on what monomers they are made from and the conditions under which they are made. For example, low density and high density polyethylene are produced from ethene. Thermo-softening polymers melt when they are heated. Thermosetting polymers do not melt when they are heated. This is due to thermosetting polymers having cross-linking bonding across the chains, which do not break easily. Most composites are made of two materials with a matrix binding together fibres or fragments of the other material, which is called the reinforcement. The Haber process and NPK fertilisers. The Haber process is used to manufacture ammonia. It can be used to produce nitrogen-based fertilisers. The purified gases are passed over a catalyst of iron at a higher temperature and a higher pressure. The reactants are hydrogen and nitrogen to react to form ammonia. The reaction is reversible, so some of the ammonia can break down. Compounds of nitrogen, phosphorus and potassium are used as fertilisers. NPK fertilisers contain compounds of all three elements, N being the symbol representing nitrogen, P the symbol to represent phosphorus, and K being the chemical symbol representing potassium. NPK fertilisers are formulations of various salts containing appropriate percentages of the elements. Ammonia can be used to manufacture ammonium salts and nitric acid. Potassium chloride, potassium sulfate, and phosphate rock are obtained by mining, but phosphate rock cannot be used as a fertiliser. Phosphate rock reacts with nitric acid to form calcium nitrate and phosphoric acid, which is neutralised with ammonia to make ammonium phosphate. Phosphate rock also reacts with sulfuric acid to produce single superphosphate, a mixture of calcium sulfate and calcium phosphate. Phosphate rock also reacts with phosphoric acid, producing triple superphosphate, also known as calcium phosphate. The Haber process. Ammonia is an important industrial product to make fertilisers, explosives and dyes. It is manufactured using the Haber process. This involves a reversible reaction between nitrogen and hydrogen. The balance symbol equation is N2 plus 3 moles of H2 forms 2 moles of NH3. The reaction can reach a dynamic equilibrium, in which the concentrations of products and reactants remain constant and the forward and backward reactions occur at the same rate. Nitrogen is obtained from the air and hydrogen from natural gas. The gases are placed in a compressor and then they react in a reactor. Any leftover or unreacted gas is placed back into the tank to be recycled. The conditions for the Haber process are compromised. The ideal conditions for the Haber process would be a low temperature and a high pressure. Low temperatures would cause the rate of reaction to be too slow. The reason why a low temperature would be preferable is because the forward reaction is an exothermic process, and low temperatures will favour the exothermic reaction. A compromise in the temperature of 450 degrees Celsius is a high enough temperature for the endothermic reaction to be favoured and for it to happen at a fast enough rate. It's passed through a tank containing an iron catalyst to speed up the rate of reaction further. The pressure is compromised due to the reaction having 2 moles of product and 4 moles of reactant. A high pressure would be the ideal condition required to produce a maximum yield of product. This is due to the product side of the reaction having 2 moles. Therefore, it is at a lower pressure, and high pressures will favour the side with the fewest number of molecules. However, in industry, making your equipment